Okay, welcome everyone. So this is our last example for the course, and I decided to do it online so that we could reach everyone and just make sure that we all have a good solution for this type of problem. This problem is looking at a beam that's subjected to loads. So we have 3 kilonewton loads at concentrated force. We have a distributed load acting halfway across the beam, and we have been given some information about this beam FAC force as well as the value for I. The question wants you to determine the state of stress for E and F respectively, put them on a stress element, and then determine the principal stresses for this type of element. I wanted to draw you into the importance of where those points E and F are. E is actually on the neutral axis, and F is somewhat superior to it, acting on the actual this post part of your I beam, and again, it's different. So remember, the state of stress will be determined by where that point is, and we know that. We've spent a lot of time talking about transverse shear is 0 at the top and the bottom. There's no bending moment at the neutral axis, so we know different forces and different stresses are occurring across this section of the beam, and so now we can kind of practice our skills at analyzing this type of problem. The first thing we always want to do is, of course, do our free body diagram for the whole beam to see what our loading is and what our support reactions are. We have our 3 kilonewton concentrated force there. We have this distributed load, which has a value of 30 kilonewton per meter, and it's acting at 0.8 meters. So the resultant force is 24. That's going to be acting at 0.4 meters from B. In this problem, we could do some of the forces in X and Y to get Bx and By. We don't actually need them for this problem, but I want to impress upon you, if you have time and you're doing great, do these equations. They're easy part marks, and you know how to do that so well. So we're going to take the bending moment at B, and so we have an FAC times the perpendicular component, so sine theta, which we can easily tell. We have all of our values for our triangle here. So we can easily measure what that angle is. Lots of 8 triangles there. So FAC sine theta times the distance at X, it's acting across the whole length of the beam, 1.6 minus 3. So I kind of changed it here. The positive is going clockwise. It doesn't matter. Remember, you just say, you say your sign convention, and the numbers will do the work for you. Then we have our 3 kilonewtons. It's going to be going in a negative bending, or sorry, not bending, a negative moment, because it's going to be causing the beam to go this way. Remember, taking it at B. It's 3 kilonewtons times the distance of the whole beam. And then we have that 24, again, also spinning the whole thing around this direction, and it's acting at a very short distance of 0.4. So we end up with FAC is equal to 15, and now we can use that in our analysis. So we need 2 points here, E and F. So we're going to start with the solution for E. Let's remind ourselves that E is on the neutral axis. Why can't I make this smaller? There we go. E is on the neutral axis, and so we need to keep that in mind when we're talking about our normal stress. So we're going to cut a section through the beam right at E. Boom. We actually know the distance of where that's occurring, 0.6 meters. And we can just add our reaction forces, our support reactions, onto the beam. And if you cut a beam, you better have an M, an N, and a V, and we do. Then you do some of the forces in the X to give you our bending moment here. So NE is equal to 15 cos theta, which is 12. Then VE, so our shear, some of the forces in the Y. I've written that out. It ends up being 6. And we do have a bending moment, or the moment E is 15. It's all right there, and it ends up to be 3.6. Then we need to be doing our normal stress and our shear stress. Our normal stress is combined of the normal force over the area which it acts, so 12 over the area. Then we normally want to include that bending moment, but remember E is exactly on the neutral axis. And remember, we know from a neutral axis that it goes from tension to compression, but on the neutral axis, there's no bending moment, so this just is equal to 0. Of course, Y is the distance from the neutral axis, and it's just 0. We're on the neutral axis. So this ends up being 3.41 megapascals. Our shear stress is being determined by our shear force times Q, which we're going to analyze down here, over I and T. I wanted to remind you as well, the V over A that we have been spending so much time on in Chapter 2, this is for the average. We now know that the shear stress really depends on where it is, right? There's no shear stress at the top and the bottom. It's maximum at the neutral axis. So this V over A was just an average, but now I'm saying, tell me exactly what it is at a particular point. So that's why we really need that Bickett equation, our shear force equation. Anyways, so our Bickett equation here, let's do Q. So we're on the neutral axis. We have two components, and I've kind of written out the math for you there. Remember, too, our distance is 50 to the bottom of that flange, and then we have to go halfway of 16, which is 8, so it's 58. That sometimes screws students up. Anyways, you end up with your value of Q. You sub it in here. You end up with 3.62 megapascals. Now, I want you to plot your stress elements. So sigma x, we determine this is actually a positive value. 3.41 megapascals, sigma y is 0, and tau, just like in class the other day, we had our shear force was acting down, and so I said your shear stress must match that on that surface or that face of the element. And so this is actually a negative tau, so it's actually minus 3.62 megapascals. Finally, they want to tell us the principal stress at E. We can do that really easily. We can draw our handy Morse circle, or we can just sub in these values here into this equation, and you end up with sigma 1 and sigma 2. Next, we're going to do the exact same analysis for section F, which is in a different spot. First of all, it's further down. And then it's not on the cross section, it's up a bit. So we got to incorporate that into our analysis. Same thing though, free body diagram for the cross section in F. We put our loads on, cut a beam, you better have an M and an N and a V, and we do. Some of the forces in X, some of the forces in a Y, and then our bending moment. Now, this is negative, so that's super interesting, and we'll come back to that later. Okay, so then what are our stress? So normal stress, N over A, we got that. 12 over area, same as last time. Then we have minus due to the formula, and we have the bending moment is 4.8 times 0.3, where that actually is acting. Oops, sorry. Oops. So this point is a bit hard to see, and I kind of zoomed in a bit. But on the flange, I guess I can draw it down here. This distance here, the beam is telling you is 20. And we know this whole thing is 50, and this is the neutral axis. So I'm using 30 because that's actually the Y we're interested in, right? The distance in the neutral axis to the point we're investigating, which is actually 30. So anyways, that's where that 3 comes from. And then I is determined here. So you end up with minus 15 megapascals. Shear force, we have our shear stress, shear stress, we need our shear force, times our QF, which I've written out for you here. Again, it's similar thought process as the first one, but it's a different Q because we're on a different point. We're going to have a different area, different Y values. So I've written that out for you there. And then I remember this part is 16, so that's the same, so the 16. And you end up with 3.28 megapascals. Then the problem wants you to solve this, or to plot this on the shear stress. Plot this on the stress element. So sigma x was a negative. So we're going to draw that into the stress element. Then tau, this is the interesting part. So I had determined that I had guessed that the shear force was going down. But then I was actually wrong. So I had determined it was this. And then our math told us it was minus 6 kilonewtons. So it's actually up. As such, our tau, so that's our shear force, F. Our tau must also match that. So that's why I drew the positive this time. So that's a bit tricky, but makes sense with our sign convention. And this is why it's a good example. So actually our tau xy is a positive value of 3.28 megapascals. Then last step, principal stress, sub in these values into this equation, you get sigma 1 and sigma 2. So this is a great problem to make sure you understand the steps, because it's a good problem for me to ask you, and it includes, statics, free body diagram. It includes shear force, normal force, bending moment, and if you had a torsion aspect to this, we can include that as well here. Then I'm asking you to plot the stress, then transform it. So it's a great question to know. So please let me know if you have any problems.